In this video, we want to check how to find the mean and variance of a Poisson distribution using the moment generating function. So first thing we will want to note is the MGF. We have the mx of t is the expectation of e raised to the power of t of x, tx. And Poisson distribution being a discrete random variable, an expectation of x is written as the summation of x p of x, and which in turn means that if I'm having the summation of e raised to the power of t of x, I will replace this x by e tx. So I will have summation of e tx and the p of x. Meanwhile, the p of x of a Poisson distribution is given by e raised to the power of minus lambda raised to the power of x over lambda factorial. So let's put all of this together in one. Then the mx of t, which is our moment, will be the summation of e raised to the power of tx multiplied by e raised to the power minus lambda raised to the power of x over x lambda over x factorial. Now, how do I go about this for us to get to where we're going? So I can basically write this as m of x to t be equal to, let's bring out e raised to the power of minus lambda because that's sort of like a constant. Then I will now write this as e raised to the power of t, then lambda here raised to the power of x, then over x factorial. Okay, so remember from exponential series, because this is more like exponential distribution, that e raised to the power of x is equals to 1 plus x over 1 factorial plus x squared over 2 factorial plus x raised to the power of 3 over 3 factorial, right? It goes on and on, which means that this can be written as the summation of x raised to the power of n over n factorial, n starting from 0 to get to n. If I should compare this particular equation, this expression here, with this one here, then I can see that e raised to the power of t lambda is like my x, and this x is representing my n, which means that I can rewrite my m of x t to be e raised to the power of minus lambda to be e to the power of lambda et as e raised to the power of t. Because if I should fit in all of this here to be e raised to the power of t, and this changes to e raised to the power of t lambda, then I will get this one. So here we are. The next thing is to find the first derivative, so we can get our mean, because mean is equals to the first derivative of the m, then we cut it to be equals to 0. So let me clear all of this so we can proceed. Okay, so now knowing that our mean is the first derivative, so we'll take the first derivative with respect to t. So obviously e raised to the power minus lambda is still a constant, times I have to differentiate the whole of lambda et. That will still be lambda e raised to the power of t, then I will still have e raised to the power of lambda e raised to the power of t here, which is the first here will be the first derivative of m, not mean yet, with respect to t. So I'll make it to take t to be 0, which is our mean. Then that would be e raised to the power of minus lambda times lambda e raised to the power of 0, then e raised to the power of lambda multiply by e raised to the power of 0. Then that would be e raised to the power of minus lambda multiplied by lambda multiplied by 1 multiplied by e raised to the power of lambda. If I should take the two lambdas, e raised to the power of lambda will be minus lambda plus lambda plus lambda here. That will be e raised to the power of 0 times lambda, which means that this is equals to lambda. And that's our mean for Poisson distribution. And that's obvious, right? Let's go ahead to find the variance of the Poisson distribution still using MGF. Now, the variance here, the variance is taking the second derivative of the m and taking t to be 0 minus the mean squared. So all we have to do is to take the second derivative and go ahead to do the calculations. So we already know that our first derivative is what we have in front here. So let's take this out here and here. Okay, so this is our first derivative. So our second derivative here would be m second derivative x with respect to t. Now I'll treat this as a product function. So I'll take this first here. So that still remains the same. So this is lambda e minus lambda e raised to the power of t. Then I'll write the whole of this back. Then plus, I'll write the whole of this back here. Minus lambda e raised to the power of t. Then I'll differentiate this one here. And that would be lambda e raised to the power of t. Then the function back. Lambda e raised to the power of t. So if I should take all of this to be 0, that means the t to be 0, then we'll have lambda e raised to the power minus lambda e raised to the power of 0, e raised to the power of lambda, then e raised to the power of 0, plus lambda e raised to the power of minus lambda e raised to the power of 0 times lambda e raised to the power of 0 e raised to the power of lambda e raised to the power of 0. Then that would be lambda e raised to the power of minus lambda e raised to the power of 0 is still 1. Then I have e raised to the power of lambda. Then plus lambda here, e raised to the power of minus lambda, e raised to the power of 0 is 1, so I still have times lambda e raised to the power of lambda. So here will be lambda, then e raised to the power of 0, this will be e raised to the power of 0, then plus, because this cancels this, then this cancels this, but I still have lambda squared. That is my second derivative with respect to t to be equal to 0. So I'm going to go ahead to fix it into the formula here. So our variance in our shell, our variance would then be lambda plus lambda squared. Now my mean is lambda, so I'll square it. This cancel this. This also shows that the variance of Poisson distribution is still lambda using MGF. Interesting, right? So yes, that's how to solve it. So don't forget to like, share and subscribe to this channel. I'll see you in the next video. Bye for now.